Hi everyone, my name is Werner and I'm going to present polynomial equation and inequalities in chapter 2. So what is polynomial equations? Basically, polynomials, these words come from poly meaning many and nomials in this case meaning terms. So it is a many terms. A polynomial equations can have constants, variables and exponent but can never be divided by a variables. So these are the example of polynomials and these are the example of not polynomials. So what are inequalities? These are the example of inequalities. Equal to, not equal to, greater than and less than. Greater than and equal to, less than and equal to. So I'm going to present chapter 2.1, which is the remainder theorem. What is remainder theorem? When a polynomial function is divided by a divisor, the remainder is PB, and when it is divided by AX minus B, the remainder is P bracket B over A bracket, where A and B are integers and there is a restriction for A, which is A cannot be 0. So these are some of the basic knowledge about the long divisions, which is this is the quotients and this is the polynomial equation, this is the divisor, and this is the remainder. Quotient form. So what is quotient form? The result of the division of a polynomial by a binomial of the form x minus b. Px divide x minus p, get a quotient, and remainder divide by the divisor. The corresponding statement that can be used to check the divisions, which is px equal to x minus b multiplied by the quotient plus the remainder. Example 1. Apply and verify the remainder theorem. Use the remainder theorem to determine the remainder when px equal to 2x cubed minus 3x squared plus 8x minus 12 is divided by x minus 1. B. Verify your answer using long divisions. So, since x minus 1 equal to 0, the remainder is p equal to 1, p1 equal, substitute 1 inside and you give these solutions and we get a negative 5 for the remainder. So when this polynomial equation is divided by the x minus 1 divisor, we get a remainder negative 5. By using long divisions, the remainder is same as the example in A, which is negative 5. Example 2. Solve for an unknown coefficient. Determine the value of k such as 3x power of 4 plus kx cubed minus 7x minus 10 is divided by x minus 2. The remainder is x. So this is the solutions. Since we know when px is divided by x minus 2, we substitute 2 inside the equations and we get this. So move here, move there, and we get a k equal to negative 2. So the value of k is negative 2. Okay, chapter 2.1, which is factor theorem. So what is factor theorem? What if we calculate p bracket b and it is 0? That means the remainder is 0. And x minus b must be a factor of the polynomials. When pb equal to 0, then x minus b is a factor of the polynomial. When x minus b is a factor of the polynomial, then fc equal to 0. Similarly, ax minus b is a factor of px if and only if p bracket b over a equal to 0. If and only if. If and only if is a term used in logic to say that the result works both ways. Here, both of the following are true. If x minus b is a factor, then p bracket b equal to 0. If p bracket b is equal to 0, then x minus b is a factor of px. So x minus b is explained as integer zero theorem, which with leading coefficient 1 and remaining coefficient that are integers. Rational zero theorem, which is ax minus b. B is a factor of the constant term of px. A is a factor of the leading coefficient of px. For example 1, we can guess that the possible factor from the last constant, which is negative positive 1 and negative positive 2. We find it by 1 multiply 24, we get 24, and 2 multiply 12, we get 24, 3 multiply 8, we get 24, and 4 multiply by 6, we get 24. So for example 2, factorize x power of 3 plus 2x squared minus 5x minus 6 fully. First, we determine the possible factor, which is positive negative 1 and positive negative 2 and positive negative 3 and positive negative 6. Then we do it one by one if the function equal to 0. So I try 2 and it is equal to 0. Therefore, x minus 2 is a factor of this polynomial equation. Then we can use two methods to find the other two factors, which is long divisions, syntactic divisions. So these are the long divisions. We get quotients and we put the divisor inside, a in the front, and we factorize the quotient to get the lowest one, which is fully factorized. So for method 2, syntactic divisions, we wrote it down the negative 2 here. So for the first digit in front, we wrote it down with the sign of coefficients. For the first one, we put it down and we multiply by here to here. So use this to minus the digit and get an 4. So 4 multiplied by negative 2, we get negative 8, and negative 5 plus 8, we get 3. So at here we get an 0, so it means no remainder. For example 3, solve a problem using the rational zero theorem. Factorize 3x cubed plus 2x squared minus 7x plus 2. First, let B represent the factor of the constant term 2, which are positive and negative 1 and positive and negative 2. Let A represent the factor of leading coefficient 3, which are positive and negative 1 and positive negative 3. The possible value of B over A are positive negative 1 and positive negative 1 over 3, positive negative 2, and positive negative 2 over 3. So then test the possible value of 1 and we get 0. Therefore x minus 1 is a factor of polynomial equations. Then we can use long divisions to factorize and use factorization to factorize fully. So these are the example. Take a look. Okay, it is done and I pass 2.3 and 2.4 to Dinesh.
X to the power of 6 minus x to the power of 4 minus 2x equals 0. So first we have to factor out the common factor, which is x, which will equal to x brackets x to the power of 5 minus x to the power of 3 minus 2 brackets equals 0. After that, we have to factor the trinomial, which is this part here, which will give us x brackets x minus 2 brackets x plus 1 equals 0. When we do that, after that we have to solve for x. So we'll get x equal to 0, or x minus 2 equals 0, or x plus 1 equals 0. And after we solve it, we'll get x equals 0, or x equals to 2, or x equals to negative 1. finding roots of a polynomial function. Solve fx equals to x to the power of 4 minus 3x to the power of 3 minus plus 5x to the power of 2 minus 27x minus 36 equals 0 by finding real roots. Point. B represents all factors of the constant term and A represents the leading coefficient. So we do B over A. A is the leading coefficient. The possible real roots are plus minus 1, plus minus 2, plus minus 3, plus minus 4, plus minus 6, plus minus 9, plus minus 12, plus minus 18, plus minus 36, which are all real roots of 36. You type the equation into your graphing calculator to get the graph, and then you choose an point from the x-axis to solve your calculations for fx. So I chose 4, positive 4, and I did the synthetic division, and you'll get a remainder of 0, so you can see that x minus 4 is a factor. Factoring by grouping, x to the power of 3 plus x to the power of 2 plus 9x equals 0. You'll get x to the power of 2 bracket x plus 1 plus 9 bracket x plus 1 equals 0. So you can put that together, which will give you bracket x plus 1 bracket x to the power of 2 plus 9 equals 0. Then you solve for x plus 1 equals 0, x equals negative 1. So x to the power of 2 plus 9 equals 0, x to the power of 2 equals minus 9, x equals square root of 9. Square root of x equals square root of 9. So this is the non-real roots. So you get 2 real roots and 2 non-real roots, which will be negative. The real roots will be negative 1 and 4, and the non-real roots will be 3 and negative 3. Real roots are the point on the x-axis, and non-real roots are the points not touching the x-axis. Okay, now I'll be talking about chapter 2.4, which are families of polynomial functions. A family of functions is a set of functions that have the same characteristics. A family of polynomial functions will have the same degree, will have the same zeros, will cross the x-axis at the same place but different for the y-axis, will have the same basic shape, will have different local max and min, some will be higher and some will be lower. An equation for a particular member of the polynomial function can be determined if a point in the graph is known. So this is a degree tree, starts at quadrant 2 and ends at quadrant 4. Has root at negative 2 order 1 and root at 1 order 2. So the parent function is fx equals minus brackets x plus 2 brackets x minus 1 to the power of 2. So these are the parent function is the main function, and the leading coefficient changes how the graph looks. The points on the x-axis will still be the same, but the y-axis changes. The zeros of a quadratic function are 2 and 4. Write an equation for the family of a quadratic functions with these zeros. Fx equals k bracket x minus 2 bracket x minus 4. K can be any real number, but k cannot equal to 0. Because if k equals to 0, then the whole equation is 0. Write equations for 2 functions that belong to this family. So you can put 3 bracket x minus 2 bracket x minus 4, or 0.5 bracket x minus 2 bracket x minus 4. So 3 basically it looks longer, and 0.5 makes it look shorter. The zeros of a quadratic function are 2 and 4. Determine an equation for the member of the family that passes through the points 1 and 2. So first you have to sub in the points 1 and 2 for x and y. So here's the equation: y equals to k bracket x minus 2 bracket x minus 4. So you sub in y 2 and the x for 1. So you get k 1 minus 2 1 minus 4, k negative brackets negative 1 times bracket negative 2. So 2 equals negative 3k, and k equals negative 1.5. Therefore, the equation will be fx equals to negative 1.5 brackets x minus 2 brackets x minus 4. Write an equation for the member of the family that has a y-intercept at negative 80. So you just have to find the point negative 80 and you sub in the 2 points for x and y. So negative 80 equals k 0 brackets 0 minus 2 brackets 0 minus 4. Negative 80 equals k minus brackets minus 2 brackets minus 4. Negative 80 equals 8k. K equals negative 10. Therefore, the equation is fx equals negative 10 bracket x minus 2 bracket x minus 4. Determine an equation for the quadratic function represented by following graph. So the degree is 4. The leading coefficient is more than 0. The parent function is k brackets x minus 4 brackets x minus 1 brackets x minus 3 brackets x minus 4. So you choose a point on the graph and then you solve in for x and y. So it will give you 2 equals k, 2 minus 0, 2 minus 1, 2 minus 3, 2 minus 4, and you will get k brackets 2 times brackets 1 times brackets negative 1 times brackets negative 2. So 2 equals 4k and k equals 2. Therefore, the equation is fx equals 2 brackets x minus 0 brackets x minus 1 brackets x minus 3 and brackets x minus 4. Okay, and now I'll pass the presentation to Anissa.
Hi guys, I'm Anissa and I'm going to be talking about chapter 2.5, which is solving inequalities using technology. In the previous slides, we learned how to solve polynomial equations by determining the roots. In some problems, the solution is a range of values. The equal sign in the equation is replaced with an inequality sign. So what is a polynomial inequality? It results simply when the equal sign in a polynomial equation is replaced with an inequality symbol. The real zeros, or x-intercepts of a function's corresponding graph, divide the x-axis into intervals that can be used to solve a polynomial inequality. So how are they solved? Polynomial equations may be solved graphically by determining the x-intercept and then using the graph to determine the intervals that satisfy the inequality. For the first example, we need to solve the polynomial inequality and round the answers to one decimal place. The inequality given is x to the power of 3 plus x to the power of 2 minus 4x minus 2 is greater than or equal to 0. To find the solution, first we need to use a graphic calculator and graph the function y equals x to the power of 3 plus x to the power of 2 minus 4x minus 2, and then we'll get this as a result. Next, we need to use the zero function on the graphic calculator. To do this, we press the second button, the calc button, and then 2. Then we'll get 3 zeros, which are minus 2.3, minus 0.5, and 1.8 rounded to one decimal place. The values that satisfy the given inequality are the values of x for which the graph is 0 or positive, or on or above the x-axis. According to the graph, this occurs when minus 2.3 is less than or equal to x, which is less than or equal to minus 0.5, or when x is greater than or equal to 1.8. An alternate method to find this would be to solve them numerically by using the roots of the polynomial equation to determine the possible intervals on which the corresponding function changes from positive to negative and vice versa. Once the intervals are established, a value from each interval is used to test if the function is positive or negative in that interval. Chapter 2.6. Solve factorable polynomial inequalities algebraically. How can we solve linear inequalities? Solving linear inequalities is similar to solving linear equations. However, when both sides of an inequality are multiplied or divided by a negative number, the inequality sign must be reversed. For the first example, we'll be solving linear inequalities. We solve the inequality and show the solution on a number line. So for solution A, x minus 4 is greater than 2. First, we move the minus 4 onto the right side, and then we're left with x is greater than 6, which is shown on this number line. For solution B, we apply the same concept. We move the minus 2 over to the right to create minus 3x is less than minus 14. Then we divide the minus 14 by 3 to get minus x is less than minus 14 over 3. Since the x is negative, we can flip the inequality sign to make the x positive, which will leave us with x is greater than minus 14 over 3, shown on this number line. For example number 2, we'll be solving the inequality x plus 2 times by 2x minus 2 is greater than 0. For method 1, we need to consider all cases. Case 1 would be x plus 2 is greater than 0, which leaves us with x is greater than minus 2, as well as 2x minus 2 is greater than 0, so 2x would be greater than 2, therefore x is greater than 1. Since x greater than 1 is included in the inequality x is greater than 2, negative 2. Since x is greater than 1 is included in the inequality x is greater than negative 2, the solution is x is greater than negative 2. For case 2, x plus 2 is less than 0, so x would be less than minus 2. And 2x minus 2 is less than 0, so 2x would be less than 2, therefore x is less than 1. Since x is less than 1 is included in the inequality x is less than minus 2, the solution is, again, x is less than minus 2. By combining the results of the two cases, the solution is x is less than minus 2 or x is greater than minus 2. The second method would be to use intervals. The root of the equation x plus 2 times by 2x minus 2 are x equals to minus 2 and x is equal to 1. Using the roots, break the number line into 3 intervals, which are shown here. Then we need to test the arbitrary values of x for each interval. For x is less than minus 2, test x is equal to minus 3. To do this, input minus 3 into the brackets where x should be. Then we'll be given 40 as a result. Since 40 is greater than 0, x is less than negative 2 is a solution. For negative 2, which is less than x, which is less than 1, test x is equal to 0. To do this, input 0 into the brackets where x would be. This leaves us with 4. Since 4 is greater than 0, negative 2 is less than x is less than 1 is a solution. All the information gathered can be summarized in this table. This table shows the positive and negative intervals of the equation. From this, we can tell that the solution is x is less than negative 2 or x is greater than 1. This can be shown on the number line. This shows all the intervals where the equation is positive. And that brings us to the end of Chapter 2, where we learned about the remainder theorem, factor theorem, polynomial equations, families of polynomial equations, solving inequalities using technology, and solving factorable polynomial inequalities algebraically. Thank you for watching.